Hi class, welcome to exercise 3E, review of index laws, where we're beginning our new unit on exponentials and surds. In this class, your examples and pre-learning are going to be exercise 10, using index law 1. And for this example, your pre-learning is questions 1 and 2 in the new book and question 4 in the old book. Then we're going to move on to example 11, where you'll be using index law 2. And your pre-learning related to example 11 is questions 3 in the new book and questions 5 in the old book. The next example will be example 12, where we'll be combining index laws. And your pre-learning for that will be questions 4 and 6 in the new book and questions 6 and 8 in the old book. And then our final example is example 13, where we'll be using the zero power. And your pre-learning questions for this example are questions 5 in the new book and question 7 in the old book. This lesson is revising what you already know, assuming that you've completed Year 9 or preparatory maths. However, it's not just revising, we're beginning to express exponentials in a way to lay the groundwork, so you're going to be able to go much deeper into this topic. The rules and laws that we're going to revise and cover in this lesson are vital. They extend your ability to count and perform algebraic operations. Fully understanding and memorizing these laws will help you find shortcuts to understanding many number properties and natural phenomena. Alright, let's move on to the introduction. Many years ago, you learnt how to count. Then you learnt how to count by more than one number at a time, often starting from another number. We call this skill addition. For example, start at 6 and count 5 more. We came up with the notation for that as 6 plus 5 equals 11. Then after that, you began to learn to repeatedly count groups of the same number. And we call this skill multiplication. For example, if 5 people have 3 pens, then we have 3 plus 3 plus 3 plus 3 plus 3 equals 15 pens. The notation we use for this is 5 times 3 is equal to 15. We also learnt some interesting laws and rules about addition and multiplication. For example, it turns out that 5 plus 6 also equals 11, and 3 times 5 also equals 15. We've learnt to call this associativity. We also learnt things like 3 times 12 is equal to 36, and 3 times 10 plus 2 is equal to 3 times 10 plus 3 times 2, which equals 30 plus 6, which equals 36. That taught us that the order of operation can matter sometimes. We call this distribution. Then we started to think about multiplying by the same number over and over again. So for example, if I was to start with $1 in my bank account and my family decides to double it every year, after 4 years, I'd have 2 times 2 times 2 times 2 equals $16 in my bank account. We call this exponentials and came up with a notation 2 to the power of 4. We can use words like indices, order or power to describe the 4 in that notation. We can use these terms interchangeably, so prepare for that. We call the number that's repeatedly multiplied, in this case 2, the base. Because exponentials were first discovered as repeated multiplication, we have some rules or laws that are a consequence of multiplication. Some of these rules or laws will also be a consequence of other laws of the exponentials. You'll notice this as I go through them. Because the index is about how many times I multiply a base, for example, 2 to the 3 is 2 times 2 times 2, then if I multiply 2 to the 3 by 2 to the 2, and then expand each exponential, I get 2 times 2 times 2 times 2 times 2. In other words, 3 repeated multiplications of 2 times 2 repeated multiplications of 2. And because multiplication is associative, if I expand all these brackets, I just end up multiplying 2 by 2 by 2 by 2 by 2, which is 5 repeated multiplications of 2. And 5 repeated multiplications of 2 is a definition of 2 to the 5. And I can rewrite that as 2 to the 3 plus 2 because 5 is equal to 3 plus 2. Okay, so this is true for any base a. So if I was to raise it to the power of m and then multiply it by the same base raised to the power of n, we'd end up with the same result. So this takes us to law 1. which is a to the m times a to the n will equal a to the m plus n. If I expand those exponentials, a to the m is a times a times a m times, and a to the n is a times a times a n times. And now we're repeatedly multiplying a m plus n times. Because we can rewrite a division as a fraction and then simplify that fraction, for example, 12 divided by 3 is equal to 12 over 3. In expanding the factors of 12, 3 times 2 times 2, we now have, and then cancelling the 3's, that's equal to 4. Or similarly, 12 divided by 4 equals 12 over 4. And expanding the factors of 12 again, that equals, and then cancelling common factors, that is equal to 3. So if we now had 2 to the power of 4 divided by 2 to the power of 2, that's actually equal to 2 to the power of 4 over 2 to the power of 2. And then to expand these exponentials, 2 to the power of 4 is just 4 repeated multiplications of 2, and 2 to the power of 2 is 2 repeated multiplications of 2. And cancelling out common factors, that becomes 2 to the power of 2. And because 4 minus 2 is equal to 2, I can rewrite that as 2 to the power of 4 minus 2. So that's a numeric example of law 2, which is a to the power of m divided by a to the power of n equals a to the power of m over a to the power of n, which equals a to the power of m minus n. So to demonstrate with some algebra why this has to always be true, we're going to let m be greater than n. So that'll mean that m has to equal n plus m minus n. Therefore, a to the m divided by a to the n will equal a repeatedly multiplied m times. And because m is equal to n plus m minus n, we can say the first group here is n times and the second group is m minus n times. So clearly in total there is m repeated multiplications. And then because we have a to the n on the denominator here, that means we have a repeatedly multiplied n times on the denominator. Now these n repeated multiplications of a are common factors between the denominator and the numerator, so we can cancel them out and we're left with a repeatedly multiplied by n minus n times, which is the definition of a to the power of m minus n. So that algebra there demonstrates why law 2 has to be true. So here's a fun fact. 4 to the power of 3 equals 4 times 4 times 4 equals 64. And at the same time, 8 squared, which equals 8 times 8, is also equal to 64. So how did I know that? Well, 4 is equal to 2 to the power of 2, and 8 is equal to 2 to the power of 3. So instead of just saying 4 to the power of 3, if I substitute in 2 to the power of 2 for 4, we now get 4 to the power of 3 is equal to 2 to the power of 2 to the power of 3. And doing the same thing with 8, we get 8 to the power of 2 is equal to 2 to the power of 3 to the power of 2. So if we're raising everything in the bracket to the left here to the power of 3, that means we repeatedly multiply that, right? In other words, 2 to the power of 2 repeatedly multiplied 3 times. And similarly on the right hand side, if I raise 2 to the power of 3 to the power of 2, that just means I repeatedly multiply that 2 times. And if we go one step further and expand this 2 to the power of 2, we're going to end up with, so repeated multiplication twice, 3 times. And on the other side, we repeatedly multiply 2 3 times twice. But in the end, we still end up with 6 repeated multiplications of 2 on both sides, and that is the definition of 2 to the power of 6. So that's a numerical example to prepare you for index law 3, which is formally stated a to the m raised to the power of n is equal to a to the m times n. We should also note that this is equal to a to the n, all raised to the power of a to the m. So to give a proper algebra justification, if I raise a to the m all to the power of n, That means I'm repeatedly multiplying a to the m n times. So as I said, some of these laws build upon each other. And here by law 1, multiplying the same base raised to a different power means we add them together. So therefore, a to the m times a to the m n times is equal to a to the m plus n n times. And here we're starting to draw a lot of connections, right? Because repeated addition is the same as multiplication, a raised to the power of m n times is equal to a raised to the power of m times n. All right, next, 2 squared is 4, and 3 squared is 9, and 4 times 9 equals 36. So that means 2 to the power of 2 times 3 to the power of 2 equals 36, right? But it also happens to be true that 2 times 3 is 6, and 6 squared is equal to 36. Now this isn't just some weird fact. This is going to work for all numbers raised to the same power, and that's because if we're multiplying numbers together, it doesn't matter what order we multiply them in. In our first lesson for this subject, we spoke about associativity. We've also spoken about it in this lesson. So 6 squared is actually equal to 2 times 3 squared, right? So squaring everything in the brackets means we multiply it by itself twice. So that's 2 times 3 times 2 times 3. And using associativity, we can reorder where those numbers are. So let's put the 2's on the left and the 3's on the right. So we've repeatedly multiplied the 2 twice and the 3 twice. So by definition, this is 2 squared times 3 squared. So once again, hopefully starting off with numbers makes it easy for you to understand, because after I give you this law, we're going to justify it with algebra again. But anyhow, law 4 is a times b all raised to the power of m is equal to a to the m times b to the m. So we can justify this with algebra, because if we were to raise a times b to the power of m, it's equal to a times b repeatedly multiplying m times. And because multiplication is associative, I can reorder that multiplication by putting all the a's on the left and all the b's on the right. And inside this multiplication, I've got a repeatedly multiplied m times and b repeatedly multiplied m times. And then by definition, we've now got a to the m times b to the m. Okay. So if I multiply a fraction by another fraction, we end up with a fraction where we have a numerator that is a multiplication of the two original numerators, and the denominator is a multiplication of the two original denominators. So in simple maths, we could say that 2 over 3 times 2 over 3 is 2 times 2 over 3 times 3. Or in other words, it's 4 over 9. Now if we look at this closely again, and I start off by writing 2 over 3 all squared. Well, that's equal to 2 over 3 times 2 over 3, which is multiplying it 2 times. And then if that equals 2 times 2 over 3 times 3, then we've got a repeated multiplication of 2 at the top and a repeated multiplication of 3 at the bottom. So by definition, that's 2 squared over 3 squared. So this is the basis for law 5. And that is a over b all raised to the m is equal to a to the m over b to the m. Let's have a go with some algebra here. So a over b all raised to the power of m is equal to a over b multiplied by itself m times. And when we're multiplying fractions together, we just multiply all the numerators with all the denominators. So that ends up with a times a m times all over b times b m times. And the numerator by definition is a to the m, and the denominator is b to the m. So we have a to the m over b to the m. So they're the 5 laws of indices that we're going to cover. I've given you numerical and algebra explanations, so there should be no dramas at all for you to understand any of it. But we've got 2 consequences of law 2 that we need to cover as well. The first consequence is, what does a to the 0 mean? Well, let's start off with the fact that anything divided by itself is equal to 1. So a to the m over a to the m equals 1. I hope you agree with that. But by law 2, a to the m over a to the m equals a to the m minus m. And m minus m is 0, so that equals a to the 0. And as I said, we justify this with law 2. So when we put these two facts together, that means that for nearly all numbers, a to the 0 is equal to 1. So why did I say nearly? Because there's one notable exception. 0 to the power of 0 is not equal to 1. You can accept that as a fact, but for those of you who are maths nuts like me, you can look up videos by Eddie Wu for more details on that. In fact, if you're a real whiz, you can see black pen, red pen, and he'll show you how to turn 0 to the power of 0 into any number you want. Enter the search in YouTube for 0 to the power of 0 and look for Eddie Wu and black pen, red pen. But the reason why I said if you're a whiz for black pen, red pen is you'll need to know what limits are though. Actually, I think I'm going to add a challenge into this video that will help paint a picture for you. Also, did I mention 0 to the power of 0 is not equal to 1? Okay, sorry to hammer that home, but it is an important fact. So you can remember that every other number other than 0 to the power of 0 is 1, but not 0. Alright, one other consequence of law 2 is that a to the power of 1 is a, and that one is true for all numbers. And to justify this with law 2, if I had a to the power of m plus 1 divided by a to the m, then I'd have m plus 1 repeated multiplications of a in my numerator and m repeated multiplications of a in my denominator. So in other words, one more multiplication at the top. So in other words, if I had m at the top, there would be this other one here. Then if I looked at m on the bottom and then cancelled out m repeated multiplications of a from the numerator and the denominator, I would then be left with just a. And then by law 2, a to the m plus 1 over a to the m is equal to a to the m plus 1 minus m. And because m plus 1 minus m is equal to 1, that's equal to a to the 1. So just by cancelling fractions and law 2, then we can show that a to the 1 is definitely equal to a. We could also look at the definition of indices. Now because a to the 3 is equal to a times a times a, or repeatedly multiplied 3 times, and a squared is equal to a times a, repeatedly multiplied twice, then the number in our index is the same as the amount of a's, right? So a to the 1 would just equal 1a. But I have to be honest, this is a little bit cheeky and not very rigorous. But either way, you can take it to the bank that a to the 1 is equal to a. In the next lesson, we're going to learn about negative indices. They're also a consequence of law 2, and a bit of law 5, but mainly law 2. It's really important that you memorize these laws, so you should take these down as notes. So I'm going to copy them in one place now. Okay, so here they all are. Some things for you to look out for. Firstly, laws 1 and 2 demonstrate that you can integrate different indices if you're working with the same base. And laws 4 and 5 show that you can work with different bases when you're working with the same indices. It's really important you're careful not to mix that up. Okay, so throughout this unit, the algebra is going to get tough at different stages. So as it gets more complicated, you need to work methodically and never forget BODMAS or BIDMAS. Alright, so I'll see you in the next section where we begin the examples. In the example I'm about to do and your pre-learning, you really only need to worry about law 1 and BIDMAS. Okay, so let's just get on to example 10, which is asking us to simplify the following expressions using the first index law. Okay, in part A, we've got the expression x to the 5 times x to the 4. There's nothing too challenging here, we're just applying the index law, which makes this expression x to the 5 plus 4, and 5 plus 4 is equal to 9. So as I said, all we did there was use law 1. There's a little bit more in part B, where the expression is 3a squared b times 4ab cubed. I can totally reorder this to 3 times 4 times a squared times a times b cubed. And the reason we can reorder it is because of associativity. So law 1 will be easier if we remember that a equals a to the 1. So now this has become very simple because 3 times 4 is 12. And by law 1, a to the 2 times a to the 1 becomes a to the 3. And b to the 1 times b to the 3 becomes b to the 4. I should also note that as you get more confident, you can skip the reordering step. But if you're not 100% confident, I do suggest you do it in the meantime, because there's no point trying to run if you're not yet walking. I know this seems simple, but you should pause the video and work on questions 1 and 2 in the new book and question 4 in the old book. And that is because it does get tougher. So this way we can make sure you get everything completed that you can. All right, I'll see you in the next section. Okay, in this section, we're going to be using index law 2. Other than law 2, in the example I do and the pre-learning you do, you only need to watch out for BODMAS and remember to convert a division into a fraction if we need to simplify. All right, let's just get on to example 11, which is asking us to simplify the following expressions using the second law of indices. In part A, the expression is m raised to the power of 7 divided by m raised to the power of 5. There's nothing challenging here, they've both got the same base, so we just subtract the power to the right of the division sign from the one to the left. So that's just equal to m to the 7 minus 5, and 7 minus 5 is 2, so that's equal to m squared. In part B, the expression is 4x squared y to the 5 divided by 8x y squared. That was really kind of them to put everything in brackets, so now we know everything to the right of the division sign is in the denominator, so we can rewrite that now as 4x squared y to the 5 all over 8x y squared. And in the future, I don't think you'll need to do this, but just for now, it might be easier if we write that x is equal to x to the 1. This might get a little bit simpler if I separate them all into 3 different fractions of 4 over 8 times x to the 2 over x to the 1 times y to the 5 over y squared. So having them separated like this does make the fractions a lot easier, right? So 4 over 8 simplifies to a half. X squared over x to the power 1 is x to the power of 2 minus 1. And y to the 5 over y2 equals y to the 5 minus 2. And that's all due to the second law. And I'm sure it's not controversial to say that 2 minus 1 is 1. And 5 minus 2 is 3. So that is equal to x to the 1, or x, times y to the 3, all divided by 2. And just like in the previous section, I think you're going to get more confident and you will skip a lot of these reordering steps. But if you're not 100% confident, I do suggest you use them in the meantime. Once again, you need to pause the video now and work on questions 3 in the new book and questions 5 in the old book. Okay, so in this section, we're going to be combining the index laws. So I've got them pre-written here. Once again, on top of all the laws, we're going to need to take notice of BODMAS. Now, obviously, we've only used 2 laws so far, and they'll all be used in this example. But let's get straight into example 12, where we're asked to simplify the following expressions using the index laws. In part A, the expression is a to the 3 raised to the power of 4. So this is just simply a matter of using law 3. So that's just equal to a to the power of 3 times 4. And 3 times 4 is 12, so that's equal to a to the power of 12. And all we've used here is law 3. So that was pretty straightforward. All right, let's go to part B, where the expression is 2 times y to the 5, all raised to the power of 3. So because of BODMAS, obviously we have to do the brackets in order first. So we need to raise everything inside the brackets to the power of 3. So that's equal to 2 to the 3 times y to the 5 times 3. And 2 to the 3 is 8, and 5 times 3 is 15. So we're left with 8 times y to the power of 15. So we've just used laws 3 and 4 in this question, but also notice how I've evaluated 8. All right, that was pretty straightforward, but it starts to get a little bit more complicated now, as you'll see in part C, where their expression is 3 times x squared divided by 5y squared times z, all raised to the power of 3. So by law 5, that means we raise the numerator to the power of 3 and then the denominator to the power of 3. Just like we did in part B, we're going to use laws 3 and 4, but this time we're going to use it for both the numerator and the denominator. So that makes the numerator 3 cubed times x to the 6. So I hope you're fine with me skipping writing out the actual multiplication of the indices now. And the denominator is going to be 5 cubed times y to the 6 times z cubed. So there's no common factors. The only step left to do is to evaluate our numbers. So that leaves us with 3 cubed is 27 and 5 cubed is 125. So 27 times x to the 6 all over 125 times y to the 6 times z cubed. I'm not sure why they think that's simplifying. It looks bigger to me. But anyhow, let's move on to the next one. Part D, where their expression is, oh my God, 3 times x times y squared all raised to the power of 3 times 4 times x to the 4 y squared. And that whole expression over 8 times x squared times y. Okay, this looks big, but let's go one step at a time using BODMAS. So brackets first, so if I expand that out using law 3, we now get 3 times x cubed times y to the 6, and the rest remains the same. Then if I use law 1 and align all the pronumerals and numbers in such a way, the step after my next one is going to be easier. So x cubed times x to the 4 becomes x to the 7, y to the 6 times y squared becomes y to the 8, and I can't do anything at the bottom. So that now equals 12 times x to the 7 times y to the 8, all over 8 times x squared y. So 12 and 8 share a common factor of 4, so that makes 12 3 and 8 2. And hopefully you're confident enough now with law 2. So I'm going to end up with x to the 7 minus 2 and y to the 8 minus 1. Putting that all together, we end up with 3 over 2 times x to the 5 times y to the 7. And that's as far as I can go with that one. Now I know part D looks a little bit ugly when you first see it. And it can also seem a little bit pointless working through all of that algebra. And these sorts of problems are where a lot of people start getting palpitations and think that they'll give up on maths. However, when you step through it using the laws that we've already learned, it's not that difficult, as long as you apply them correctly and pay attention to BODMAS. You'll come up with equations like this doing all sorts of problems in business and science later on in life, as well as other topics in your math study. So if you work hard at it now, you'll end up a mathematics legend in no time. Well, speaking of hard work, that's a perfect segue, because you should really pause the video now and work on questions 4 and 6 in the new book and questions 6 and 8 in the old. And then I'll see you in the next section. Okay, so it's time to be a hero with the 0. Anyhow, back on track, we need to remember that anything raised to the power of 0 is 0, except 0. So 0 is the anti-power of the 0 hero. So despite the confusion we can get with the 0, it's still pretty straightforward as long as you pay attention to BODMAS. Sorry to say that for the 4th time, but a number of students have got these questions mixed up in the past. But let's just move straight into example 13, where we have to evaluate the following expressions using the 0 power. And the expression we have in part A is 4 times a to the power of 0. So a raised to the power of 0 is 1, so therefore that's equal to 4 times 1, which is equal to 4. Okay, in part B, the expression is 2 times p to the 0 plus 3p all raised to the 0. Okay, in case you haven't already guessed it, this is the question that a number of students have got wrong in the past. If you don't use BODMAS and law 4 here, you probably will make a mistake. But if you do use them, it's really simple. So paying attention to BODMAS means we focus on the brackets first, and law 4 means that I'm going to raise 3 to the 0 and p to the 0. So that means we now have 2 times p to the 0 plus 3 to the 0 times p to the 0. So obviously p to the 0 is 1 and 3 to the 0 is 1. So we've now got 2 times 1 plus 1 times 1, which equals 3. And let's not forget we used BIDMAS there and law 4 in the next step. And as I said, if you stick to that, you won't have any confusion. It's time for you to pause the video here and work on question 5 in the new book and question 7 in the old book. And that's the end of the last section with the examples. I'll see you in the summary. Okay, let's summarize this lesson now. So to consider this lesson a success, when you complete it, you will know that powers are used as a shorthand way of writing repeated multiplications. Understand that the index laws for multiplication and division apply only to common bases. Know how to combine powers with the same base under multiplication and division. Know how to apply powers where brackets are involved. Know that any number except 0 to the power of 0 is equal to 1. and to be able to combine a number of index laws to simplify an expression. Just before we wrap up or move on to the challenge, we saw that combining the laws can be grounds for confusion, but with persistence, you'll be able to master that. By breaking down all of the problems into little steps, you'll be able to conquer them one by one. But also make sure that you note down all of the laws for your reference material. But don't just write them down without making sure you understand why each law is true. Okay, well, let's keep up the great work, class. If you don't want to stick around for the final challenge, I'll see you in the next class or the next video. In fact, I'll see you in the next video because you need to watch 2 for this class, okay? Anyhow, now for the challenge. Earlier in this lesson, when I said 0 to the power of 0 is not equal to 1, did you notice that I didn't use the not equal symbol? Well, that's because it's a little more subtle than that. To help you figure this out, it might be a hint if you try and recall the no solutions in simultaneous equations. In BCE, you'll learn all about limits. They are all about what a function is going towards as it approaches a number or heads off to infinity. So in this challenge, the functions we're going to use are: number 1, y equals x to the 0. Number 2 is where y equals 0 to the power of x. And the last one, number 3, is where y equals x to the power of x to the 0.6 or x to the 0.2 is. However, at this stage, you can just trust the calculator. So some possible examples you could come up with these functions are y equals 0 to the 0.9 or y equals 0.9 to the 0.9. And normally in a calculator, we use that arrow symbol to indicate indices. So here you can see I have 0 to the 0.9 and 0.9 to the 0.9, and if I evaluate them, I come up with the results where, no surprises, 0 to anything is 0, and 0.9 to the power of 0.9 is this number that's nearly 1. So we can now make a table like this with x values of 2, 1, 0.5, 0.2, 0.1, 0.001. Underneath that we can write the function names and close off that table. And if you substitute these different values of x in for x in these functions, you'll be able to see what this function is getting closer to as x gets closer and closer to 0. I've graphed these functions, but don't look at it now. Have a go at this first, but if you do need to look at it later, this is the link here. Okay, so that's the setup for the challenge. So the questions for you are: question 1, when x is equal to 0, what is y equals x to the 0, y equals 0 to the x, and y equals x to the x? And for this question, I just want you to sub in x equals 0. Question 2 is, what do each of the functions seem to be approaching as x gets closer and closer to 0? And the last question is, what do your answers to questions 1 and 2 tell you? Okay, well, good luck with that. I thought this lesson would just be fairly dry algebra, but I suppose there's always something interesting to find in every maths topic. All right, I'll see you in the next video. See ya.